Hi, so this is the second of a few test videos just to get some footage to figure out how I'm going to eventually post more edited, cleaner, professional videos to the site. But I thought I'd entertain you all with a math problem that I actually dreamed about one time. And it was a question that occurred to me in the middle of my sleep. Woke up in the middle of the night and I thought that's actually a valid question. And the question was, how many rational numbers are there greater than zero? That is, how many positive fractions exist? Of course, you can't really count them all. There's infinitely many. And so this was part of my dream. You might call it a mathematical nightmare of sorts. But then other questions started to emerge in the dream. And as I woke up, I started to explore the questions even further. And what I want to do is consider a paradox, present it to you, and ask you, the viewer, to figure out how do you resolve this paradox. So here it goes. I want you to consider a number line from 0 to infinity. Okay, and what we're looking at is all the fractions that are positive fractions, everything greater than 0. We're going to divide this number line up into sections. We're going to partition it with units of 1. And you can imagine the unit line continuing indefinitely in the positive direction. So let's suppose that we considered all the fractions between 0 and 1. What we're going to do is actually compare the fractions between 0 and 1 to the fractions between 1 and 2. And it would seem that over the span of 1 unit on the number line, we would actually have the same number of fractions between 0 and 1 as we have between 1 and 2. In fact, one way to confirm that the number of fractions between 0 and 1 is equal to the number of fractions between 1 and 2 will be to simply pair them up. And so I want to consider comparing sets of fractions. So comparing the set of fractions between 0 and 1 to the fractions between 1 and 2, we can imagine ourselves picking any fraction between 0 and 1. So let's just take as an example 2/3. Okay, and then to the fraction 2/3, let's add 1 to get the fraction 1 2/3, or 5/3. And in this way, every fraction between 0 and 1 can be paired with a fraction between 1 and 2. We can say that there's a 1-to-1 correspondence between the two sets of fractions, and in that sense we can say that the number of fractions between 0 and 1 is equal to the number of fractions between 1 and 2, as they can perfectly be paired with one another by simply adding 1. So we'll call this a mapping of numbers in one set to numbers in another set. That can go either direction by adding or subtracting 1. We can move back and forth, pair them perfectly with one another, and conclude that there's an equal number of fractions in both sets. So I'm going to call this plus or minus 1. I'm going to put an arrow on both sides to say that we could go back and forth. So in that sense, we would say that these are actually equal to one another. The fractions between 0 and 1 are equal to the fractions between 1 and 2. But let's not rush to conclusions, because there's another way to pair fractions. And so in this case, we're going to run into a paradox, because now I want you to take any fraction greater than 1. So let's erase our first pairing. That is our mapping from 2/3 to 5/3. And now let's look at the set of fractions greater than 1. And compare that to the fractions between 0 and 1. Okay, what we're going to attempt to do is in the same way that we did before, as we mapped fractions from one set into the other by adding or subtracting 1, we're going to come up with a similar mapping to map numbers in one set here to numbers in the other set. We're going to see if we can make a one-to-one pairing, and in fact we can. And that's through the mode of multiplicative inverses. So let's pick any number greater than 1. So let's say we've got a number like 2.5 or 5 halves. I'd like to make the claim that 5 halves has a unique multiplicative inverse. There's only one other fraction, or one fraction that we can multiply by 5 halves to get 1. And that other fraction can be found by simply reciprocating 5 halves. Well, when we take anything greater than 1 and we reciprocate it, it ends up landing between 0 and 1. So for example, 5 halves reciprocated is 2/5. And so in this sense, we are actually pairing fractions together according to their multiplicative inverses. Now, can we keep doing this forever? In fact, we can. For any fraction greater than 1, it doesn't matter where it is. Let's pick something, way out here on the number line. Let's say we've landed at, say, 99. Well, all I have to do is reciprocate 99. I get 1/99th. And where does that land? Between 0 and 1. So it appears to be the case that for every fraction greater than 1, there is a unique multiplicative inverse between 0 and 1. And in that case, if we can compare them in this way, mapping from one fraction to its multiplicative inverse, we can say that the number of fractions between 0 and 1 is equal and sufficient to be mapped to all of the fractions greater than 1. And I can put an equal sign here as well. This, of course, is the paradox. How can there both be an equal number of fractions between 0 and 1 as there are between 1 and 2, but also be enough fractions between 0 and 1 to be mapped by multiplicative inverses to all fractions greater than 1? It would seem that there's a paradox here. And so the question that I would pose to you as the viewers, can you resolve this? I invite you to offer your comments on how this paradox is resolved. It's a little bit bizarre. In my own attempt to resolve this paradox, I actually stumbled upon the golden ratio. So if that sounds enticing to you, explore the question a little bit and see if the golden ratio pops up in your exploration. Thanks. Bye.